Okay, guys, welcome back. Let's talk about the next Aufgabe, Aufgabe 3 from the Probeklausur, summer semester 2020. Before we start with this Aufgabe, I just want to say a few things just to bring some intuition to the question in case you have no idea what eigenvector, eigenvalue, and all these things are. You don't have to know it, but I think it's nice to have a little bit of intuition so that the questions don't seem completely alien to you. If you already know what eigenvector and eigenvalue are, feel free to skip this part. Okay, so I guess we should start with ax equals b, right? This is like the logo of linear algebra, where you have a matrix A and you multiply it with this some vector x, and out comes a vector b. In that sense, x can be viewed as the input and b is the output. So a is like your function. So a function takes an input and returns an output. And that's precisely the whole idea of eigenvectors, eigenvalues, and eigenspaces. The idea is this: x is not just one single variable, but it's a vector, right? A vector, and if you imagine a vector, it's like a line in space, right? And there's going to be some vectors, so some inputs that once you put it into the function A or the matrix A, the output is going to be another vector with a different direction. So you can imagine that the vector has been rotated a little bit, all right? But there's going to be some vectors where you put it into the matrix A, feed into the function, and the result that comes out does not change its direction. So it's still going to be the same vector in the same direction, but bigger or smaller, all right? And that's what an eigenvector is. It's the vectors that go in and don't get their directions changed. The eigenvalues is just the scaling factor of the eigenvector. We said that an eigenvector can go in and come out bigger or smaller, and how big or how small it gets is the eigenvalue. And eigenvalue, I don't have a lambda on my keyboard, so there you go, sorry. So that's, lambda would be your eigenvalue, which is the scaling factor of your eigenvector x. All right, and yeah, that's it for now. So let's get started. So whenever you want to solve some equation like this, you always have to start with, well, I'm not sure if you always have to, but here we're going to start with finding the eigenvalues, and then we find the eigenvectors. Okay, so let's take a look at the question. And yeah, the question, they're going to give us some, ignore everything else, just look at the matrix. They're going to give us some matrix. It was a 6 minus 3, 0, minus 6. It's basically this matrix, but without the minus x along the diagonal. And the first part, they're going to ask us to find the characteristic polynomial of A. And the characteristic polynomial of a matrix is just the matrix itself, but you subtract the eigenvalues x from the main diagonal. This formula says basically that it's going to be the determinant, that's what these lines mean, of A minus the identity matrix, which is the, in this case, a 4x4 matrix with zeros everywhere except for ones along the main diagonal, multiplied with the unknown eigenvector x which is effectively just x's along the main diagonal and zeros everywhere else. And if you subtract that from your original matrix, in effect, what you're going to get is this, right? You're going to get your original matrix, except that you have to subtract the unknown eigenvalues that you're looking for. And of course, you get to take the determinant of that. And whatever comes out of this, that's going to be your characteristic polynomial. So here, essentially, we're trying to find again, the determinant of a matrix, but this time it's a bigger matrix than in Aufgabe 1. It's a 4x4 instead of a 3x3. But nevertheless, we're still going to use the same technique to find the determinant of this matrix here. It's called the cofactor method. If you don't know what the cofactor method is, I encourage you to pause the video and YouTube it. It's very simple. You'll figure it out pretty quickly. So, assuming that we all know what the cofactor method is and how it works, let's do it, yeah? The idea of the cofactor method is, of course, we can strike out any row or any column, but it's always better for us to strike out the row or column that has the most number of zeros in there. Obviously here, guess what? It's easy to see. It's the third row that has the most number of zeros there. So we're going to choose the third row as the row that we strike out, all right? And once we strike out the third row, then we have to strike out each column one by one. But what happens when you strike out the first column? Well, you know, when you strike out the first column and the third row, you're going to get 0. It's called this cofactor, multiplied by the minor matrix, which is made up of these entries and this one, right? Because you don't include the row and column you strike out. So it's going to be 0 times this one and this one. And again, I repeat, don't forget your sign map, guys. It's a positive 0, all right? But positive 0, negative 0 doesn't matter because everything's 0 anyways. Then it's going to be minus. And why is it a minus? Because the sign map is a minus in this position. So minus 0 times the little matrix you get from excluding this row and this column, that plus this cofactor times the little matrix you get from excluding this column and this row, right? And then again, it's a minus 0 plus its minor matrix. Times it's the determinant of its minor matrix. But in any case, if you look at this, you should go right away, okay, you see zeros, zeros, and zeros, so they all go to 0, and in effect, you only have that, right? And I repeat, it's the determinant of this matrix times the 1 minus x. So we're going to do that here, all right? Here, again, I strike out this row, okay? I strike out this row and then each of the columns one by one. So if you strike this row and then start striking the first column, it's going to be minus 6, yeah, times the minor matrix here, or sorry, determinant of the minor matrix, minus 0. Again, don't forget your sign map, guys. It's a plus minus plus. So 0 times the minor matrix, that and that together, plus this one and this one. All right. Yeah, and then of course, when you have 2 by 2 matrices, it's going to be simple to find its determinant because it's just the product of this diagonal minus the product of that diagonal. All right. So of course, this thing goes to 0. So in effect, you only have this one plus this one. And that's what I do here, right? It's minus 6 times the product of this, which is 12, minus the product of this diagonal, which is a plus 2x, plus the 2 minus x comes down here, and it's the product of this, right, which is minus 24 minus 2x plus x squared, minus the product of this diagonal, which is minus 36. Then from here, it's easy, but tricky. Easy because you just have to simplify, but tricky because you can make lots of mistakes. I did this 7 times before I got the right answer. If you're stuck, just ask Wolfram Alpha, all right? So you simplified and simplified and simplified, and then you'll end up with some huge polynomial like this, which you have to factorize. So, well, you factorize. How do you do that? Obviously here you can take out an x, so that's what I did. You take out the x, factor out the x, and now you've got to factorize this polynomial here, and the question is, how do you do it? I think most of us know this. You just do a guessing game, right? The factor is going to be the value that makes the polynomial equal to 0. So if you do a guess, start with 1, okay? If x is 1, this whole thing becomes 0 because 1 minus 5 is minus 4, plus 8 is plus 4, minus 4 is 0. So, okay, so if 1 makes that 0, it means x minus 1 is a factor, and I wrote that here. It's called the fundamental theorem of algebra. Since when x equals 1 makes the polynomial 0, x minus 1 is a factor, all right? So once you've identified that x minus 1 is a factor, then you just do polynomial division, and I do that down here, right? Now, x minus 1, divide that into your polynomial here, and then out comes x squared minus 4x plus 4. And then again, you do you can either factorize directly if you can see it, or if you can't, well, take a guessing game as well and see. 1 doesn't work because that won't equal 0. Minus 1 doesn't work, but 2 works because 2 squared is 4, minus 8 is minus 4, plus 4 is 0. Fair enough. So x minus 2 is a factor, and in case you couldn't factor that immediately, you can do it using the polynomial division method as well. And out comes x minus 2 and x minus 2. All right, so your overall factor becomes x minus 1, and x minus 2 squared. So that's your final answer. That's your characteristic polynomial. All right, and there's plenty of places that you can make a mistake. So I guess the way that you know, or you can guess you've made a mistake, is when you try to factor your polynomial. If you can't factor it using 1, minus 1, 2, or minus 2, and sometimes 3 or minus 3, then you've probably done something wrong. Because usually x minus 2 is one of the factors, because they shouldn't make it more difficult than that. All right, so that's the answer, guys. And let's recap that. How do we get here? We took the original matrix, but we subtracted the minus x from the main diagonal, and we took its determinants by using the cofactor method. That's it. That's a characteristic polynomial of any matrix. All right, and we're going to need this part correct so that we can find the part B. And part B, I think, looks like, let me hide the, okay, part B. Here in part B, now they ask for the eigenvalues. And again, let's recap what an eigenvalue is. If you have a matrix AX, a matrix A and vector X, right? It's going to, yeah, it's the values, it's the scaling factor of the eigenvectors. And the eigenvectors are the vectors that multiply with the matrix and don't get their directions changed, okay? So if X is an eigenvector, B is just going to be a larger or smaller version of that vector. And how large or how small it is, that lambda is going to tell you that. The eigenvalues, lambda, are going to tell you that. Okay, so how do we find the eigenvalues? They're simply the zeros of the characteristic polynomial. which we found in part A. So here's our characteristic polynomial. The zeros are easy to read off, right? When is this equal to 0? Well, when x is 0, the whole thing is 0. Or when x is 1, the whole thing is 0. Or when x is 2, the whole thing is 0. All right? So that's obvious here, I think. No brainer. 0, 1, or 2. And those are your answers. All right. Here I wrote x3 equals x4 because it's x minus 2 appears as a factor twice, so you could consider them as two instances of the same eigenvector. So yeah, part B, done. Next part C, is where they ask for the eigenvalues, right? So now we found the lambdas. Here they're written as x, but they're essentially the eigenvalues, the scaling factor of the eigenvectors. Now we have to find the eigenvectors that belong to those eigenvalues. One thing I didn't say earlier, which I should have, was that every eigenvalue has its own set of eigenvectors. So that means we're going to have to look at each eigenvalue one by one and find the eigenvectors for each of your eigenvalues. You can think of them like as a little group of their own, like, right? There's a group of eigenvectors that belong to eigenvalue 0. There's another group of eigenvectors that belong to eigenvalue 1, and the eigenvectors that belong to eigenvalue 1 are the eigenvectors that are multiplied by 1 when they get multiplied with a matrix. The eigenvectors that belong to eigenvalue 2 are the vectors that get doubled in size when you multiply them with the matrix A. Anyways, so that's what is written here. Every eigenvalue has its own set of eigenvectors. It's not just a set, it's actually it happens to be a space as well. So that's where eigenrealm comes in. Eigenrealm is eigenspace, but let's talk about that later. For now, let's just focus on finding the eigenvectors for each of these eigenvalues. And yeah, so, okay. So first, let's find the eigenvectors for eigenvalue x1 equals 0. And how do you do that? Well, you remember another formula, which you don't have to remember if you see how it works, but you know what, forget it. Let's see how it works first. So to find the eigenvectors that belong to eigenvalue x1 equals 0, you subtract the eigenvalue from your original matrix along the main diagonal. So your original matrix was the black letters, and eigenvalue x1 is 0, so you subtract that from the main diagonal. And that's essentially what the meaning of this is, right? It's your matrix A minus the identity matrix, which is 1 along the main diagonal and 0 everywhere else, times that particular eigenvalue that you're solving for. In this case, our eigenvalue is 0, so it's 0 times the identity matrix, which makes everything 0, so A minus 0 is really just A, your matrix A. Anyways, and so you just got to solve this, and solving means Gauss elimination. And here it's easy. I use the pivot principle, right? You know, we want to get zeros here, and zeros here, right? So I'm going to take that element as a pivot because I'm going to use it to clean out everything below it. So if, you know, first I got to get a 0 here. How do I do that? I can take one of this away from 2 of that. So 1 of the first row subtracted from twice of the second row. And if you look at that, the new second row is going to be not subtracted, added to, sorry. It's in one of the first row added to twice the second row. That's going to neutralize this -3 and give us a 0, which it's done here, right? And of course, I also need a 0 down here. So if I just add the first row, add my pivot to the -6, I'm going to clean out the -6 and get a beautiful 0 down here, right? Just make sure you work through it carefully and you have lots of practice with lots of matrices. I encourage you to do all the past papers. So once that's done, now the next pivot is the next element of the main diagonal, and that's this 4 over here. And we need to use this pivot to clean out the 12. Well, that's going to be easy. If we take 3 of the pivot away from the 12, we're going to get a 0. And that's what we do here, right? 3 fours away from 12 is 0. 3 negative 14s away from negative 49 is -7. And 3 zeros away from 0 is 0. So the next pivot is here, -1 now. And we're going to use this, sorry, pardon me, it's a 1. We're going to use this 1 to clean out the -7. Once you clean out the 7 with a -1, you get something like this. And you do that by adding 7 of this pivot to the -7, and that's going to clean out your bottom row. All right. In this case, we don't have another pivot because a pivot cannot be 0, okay? So our matrix here has only 3 pivots. We're essentially done with elimination here. With the Gauss algorithm, it's already in row echelon form, but looking at the matrix, it's easy to see that you can clean it out even more. For example, you have a 1 here and zeros everywhere else. So I see that I can use this 1 to clean out the -14 quite easily, right? So I attempt to clean it out. You don't have to if you don't want to, but I think it's a little bit neater if we do it first. The first thing I do is, well, 4 and -14. Let's multiply that by 1/2 to make it smaller. So it's 2 minus 7. Then now use this 1 to clean out the -7. So then you get a 0 here. And also, of course, use, I also divided this row by 2 to get this. And then I used, again, the 1 to clean out the -7. This one, clean out this -7 as well as this -7. And that's a bird. Sorry about that. Yeah, and then of course you can also use this 2 to clean out the 4, which I didn't do. I'm happy, I said I'm happy enough with this matrix here. And here are your pivots, right? The pivot is the first non-zero entry in each row. So that's the first non-zero entry in the first row, first non-zero entry in the second row, first non-zero entry in the third row, and the fourth row does not have a pivot because it does not have a non-zero entry. All right. Then after you have this, then you've identified that these are your pivots, and this, so your pivot columns are here, and this is your free column. And now you're gonna solve the equation, right? So what do we have here? We have a 3a plus 4b minus d equals 0. And we have a 2b equals 0. And we have a c equals 0. All right, fair enough. So c is equal to 0, b is equal to 0, and a is equal to 4b minus 4b, but that's 0. So 3a is equal to d, so a is equal to d over 3, right? The idea is, when you have a matrix, remember to identify your pivots and then just write your pivots in terms of the free variable or your free columns. So here our pivots are a, b, and c, and I've written them in terms of the free variables. A is now in terms of the free variable d, and c and b don't have to be written in terms of free variables because they're simply equal to 0. So you're good with that. So then let's form your final answer, right? And of course, your free variable always equals itself. So if you had, imagine you had only 2 pivots and 2 free variables, then C equals C and D equals D, all right? Then your answer is going to be some vector, and your A is going to be 1/3 D, your C is going to be 0D, your B is 0D, and your D is D equals D, so D equals itself, right? And I don't like fractions, so I enlarge it a little bit and I say, okay, that's a 1 and that's a 3, right? Multiply this by 3 and you'll get 1003 times D. So that's one of your eigenvectors, and it's an eigenvector that belongs to eigenvalue x1 equals 0. But we've got 2 more eigenvalues to take care of, and we do that here. Here, if you try to solve it, again, it's hardly the same. You subtract the eigenvalue that you're solving for from the main diagonal. Once you subtract that, you're going to get this matrix. And you're going to quickly see that using the regular pivot technique that I used up here is going to give you such ugly values. 5 and -3, you can't do that. You're going to have to like multiply this by what? By 3, multiply that by 5, multiply that by 5, multiply that by 6. It's ugly. So we're going to try to clean it up in another way. All right. So just to, you know, keep things in perspective, I decided to bring the rows of 0 down to the bottom here, and I switched up the 4th row into the 3rd row. So I've switched the row 3 and row 4. Now it's easy to see. I still need to get into row echelon form, so that means I still need to get 2 zeros down here, right? And I can simplify my work by using this -3 to knock out the -6. So if I subtract twice of this away from that, it's going to give me a 0, right? So the new row 3 is twice of the old row 3 minus the row 2. And I do that because it's going to give me a 0 here. Incidentally, it also gives me nice round numbers here. Then I still have to get a 0 down here, and here I have no choice but to use my pivot. All right. So yeah, you do that by, you know, what's a common multiple? 15, I suppose. So it's 5 of this plus 3 of that is going to give me a 0. So 5 row 2 plus 3 row 1 is going to give me the new row 2. So now that column is clean. Now I've got to clean out this column. How does that work? Well, again, I've got ugly numbers here. I can't just simply use pivots to clean it out nicely. But what I could do is I could get a nice 1 over here, right? Because if I subtract 1 of this away from that, I'm going to get a 1 here. So 11 minus 10 is 1. Minus 42 minus 35 is -7 and 0. And you do that here. And now you see that the 1 can now be used to clean out the 10 below. So here they're just trying to separate students that really know their elimination from students that don't know their elimination. You just have to practice it and see it, guys. All right. If you have to do some crazy weird fractions, you're probably going the hard way, or you're doing it wrong altogether. All right, so I use this 1 to clean out the 10, right? And the 10 below, and I also use this 1 to clean out the row above, because it happens to be that I can. So the new row 3 is going to be this row 3 minus 10 row 1. 10 row 2, sorry. And that's going to give me this row. And the new row 1 I can, sorry, I'm using this -7 to clean out the -14. And that's going to give me this 0 over here. Now, if you observe, we obviously have this column, and this column clean. This column is also clean. So actually, we are done with elimination if we want to be. But I think it's always nicer to clean it up a little bit more. And if you clean it up a little bit more, you'll get this. I divide this row by 35, divide this row by 35, by what did I do? Yeah, by sorry about that. The new row 2, I get it by adding a fifth of row 3 to it. You clean it up, and now you can identify your pivots, which are the first non-zero entries in each row of the matrix in echelon form. Echelon just means stairs. So here it's like a stair. So here's a staircase over here. If this was a pivot, then if this wasn't 0, then the staircase would be here. But since it's a pivot, it's not a pivot. Your staircase is like that. All right. And how do you know which column has a pivot and which column doesn't have a pivot? Well, obviously this row doesn't have a pivot because it doesn't have any non-zero entries. So this column doesn't have a pivot anywhere, right? So this is going to be your free column, and this is going to be your pivot columns. And then the same idea applies. You're going to write your pivot columns in terms of your free columns, or your pivot variables in terms of your free variables. So C is 1 over 35D, B is 1 over 5D, and A is 0, and D equals itself because free variables always equal themselves. So with this information, we can now construct our vector, right? A, B, C, D. A is 0, we know that. D is 1D, D is D, and B is 1/5 of D, and C is 1/35 of D. But fractions are ugly, so we multiply them by the common multiple, right? To get this. That is your eigenvector that belongs to eigenvalue x2 equals 1. And this note here is just what I said earlier. In solving this equation, I didn't use the pivot principle that I use here. Usually I'd start with this pivot idea, using each pivot to clean out the rows below, but it's not always the smartest idea, because if you try to do that with this particular matrix, you'll make mistakes, and because you're going to be working with huge fractions. So the idea is you just have to practice and start seeing. For example, you have to start seeing that you can use this -3 to clean out the -6. You have to start seeing that you don't have a choice here, and you just have to use the common multiples to clean out the -3. You have to start seeing that the 10 and the 11 can, help get you a 1, which is a beautiful number to have because you can use it to clean out anything. Okay. So that's your second eigenvector, and your third eigenvector is going to be for the eigenvalue 2. And again, you subtract the eigenvalue from the main diagonal, you get this matrix. And here you just do some more elimination. I think you guys are familiar with that by now. Here again, -3, -6. Guess what? Use the -3 to clean out the -6. Yeah, and you do some elimination and you get that. Okay, so out comes another vector. So you've got 3 eigenvectors now, right? You have your 1, 0, 0, 3, 0, 7, 135, and 0, 1, 0, 6. So they're your eigenvectors, but the question was asking for the eigenrealm, eigenspace. The eigenspace is essentially the linear combinations of the eigenvectors. So let's think about that. We have one of our eigenvalues was x equals 0, right? We said that it has the eigenvector 1, 0, 0, 3. But it doesn't just have to be 1, 0, 0, 3. It can be any multiple of 1, 0, 0, 3. It can be any multiple, so that means any linear combination of 1, 0, 0, 3. And so you can have 2, 0, 0, 6, 3, 0, 0, 9, minus 1, 0, 0, minus 3, for example. Though any of those belong to the eigenvalue 0. And all the possible multiples of 1, 0, 0, 3 are valid eigenvectors for the eigenvalue x1 equals 0. But they're asking for a basis of the eigenspace. And basis just means the minimum vector that you need so that you can create the entire eigenspace. And it's called a space because it's created from one vector and all the linear combinations of that vector, so all the multiples of this vector create the eigenspace of eigenvectors that belong to this eigenvalue. And the basis is just this one alone, right? We don't write it as we don't write the D here because D is the combination. It's not the eigenvector itself. And you do the same for the other eigenvectors. Eigenvalues. I hope that was somewhat clear. If it's not, I encourage you to Google mathebibel.de and Eigenvalues. There's 3 very easy explanations to read, very short. It'll give you a lot of intuition for that. Now, the last part of this exercise is they ask for the multiplicity, Vielfachheit of each of your eigenvalues. So there's 2 types of multiplicities or Vielfachheit. There's the geometric and there's the algebraic. All right. What's a multiplicity, first of all? They're just how many times something occurs. What does that mean? So first, let's look at the algebraic multiplicity. It's just how many times, I should say the algebraic multiplicity of an eigenvalue. It's just how many times that eigenvalue appears in the polynomial, in the characteristic polynomial. So it's the power of the eigenvalue in the characteristic polynomial. So if we go back to our characteristic polynomial, we have 3 eigenvalues. This eigenvalue appears once, this eigenvalue appears once, this eigenvalue appears twice. So the algebraic multiplicity for this one, for x equals 0, is going to be 1. The algebraic multiplicity for eigenvalue 1 is going to be 1 as well. But the algebraic multiplicity of the eigenvalue 2 is going to be 2 because its factor appears twice in the characteristic polynomial. So that's the algebraic, all right? So 1 for 0, 1 for 1, and twice for the eigenvalue 2. The geometric multiplicity is going to be the number of vectors in the base of the eigenrealm. So you're going to answer the geometric multiplicity, you look at your answer from the previous part. Here, for the eigenspace of eigenvalue 0, it has one base. 1, 0, 0, 3. That's the only base. So the geometric multiplicity of this eigenvalue, 0, is going to be 1. The geometric multiplicity for the other eigenvalues are also going to be 1. But